So every linear operator has what's called an adjoint, which is a very important thing for understanding how the operator itself works. Unfortunately, in order to define one, you really need the notion of an inner product, and that's the subject of chapter 6, which we are skipping. And then adjoints are studied in chapter 7, which we are also skipping. So I'm going to give you the quick and dirty version right here. So suppose that we've got a linear map, T, and suppose that it has the matrix in with respect to some basis for V and some basis for W is A. So in general, A here is going to be an M by N matrix. So I didn't say this at the outset, but we assume V and W are finite dimensional. Adjoints exist for the infinite dimensional case as well, but it's easier just to talk about matrices for the moment. So we'll stick with finite dimensional. So then the adjoint of T, oh, that looks like a apostrophe, but there's no apostrophe there. The adjoint of T is the map T star, which is a linear map from V to W, so going in the opposite direction. And we can think of it as being defined as the operator, or sorry, the linear map whose matrix is the transpose of A. And if it's complex, we need to take the conjugate transpose. So like I said, this this only works for V and W finite dimensional. For the infinite dimensional case, you need the idea of an inner product. So an inner product is a mapping that looks like this. So you take a pair of vectors and you put them in some angle brackets like this, and the inner product that you're most familiar with is just the dot product. So more generally, an inner product, so something that takes blank comma blank. So this is going to be a map from V cross V, because it takes two variables, right? You've got one from the first guy going in here, and then you've got one from the second guy going in here. So it's a map from two variables to the underlying scalar field. So the result of an inner product is always a number. And it needs to satisfy certain properties. So it has to be the case that if you have AU plus BV as in the inner product against W, that it's linear. So this means that this is AUW plus BVW, so that it basically distributes and that you can pull scalars out. You also need it to satisfy the property that UV is equal to VU unless it's complex, unless F is the complex field, in which case you need to have a conjugate over there. And this means also, by the way, that if you have a scalar in the second component, it comes out with a conjugate sign. And then you also need it to be the case that the inner product of U against U is always non-negative, with UU equaling 0 if and only if U is actually the zero vector. So here this is 0 the number, and this is 0 the vector. Okay. And then once you have all this, you can do a bunch of stuff. You can talk about geometry, you can do projections, so on and so forth. One of the big things that you can do with it is you can define what the length of a vector is, and that's defined to be the square root of the inner product of u with itself. And then you can talk about how far apart vectors are. So we say that the distance from u to v is the magnitude of u minus v, which is then defined by this formula right here. And this gives us a well-defined notion of distance and lengths and so on and so forth. And we have some idea of orthogonality, and you can do geometry, and everything is a great, lovely place. Like I said, it's a long song and dance. That's all of chapters 6 and 7 and so forth. So for us, the most familiar example is that when v is equal to Rn, we usually take the inner product of u and v to be something where we take the kth coordinate of u and the kth coordinate of v, and then we add them up. However, you can also do this for infinite dimensional things. So let's take v to be the continuous functions on the interval from 0 to 1. And so then the inner product between u and v, oh, I forgot to mention, that one is often denoted u dot v. Or if you're thinking of these in terms of matrices, this is the matrix of u transpose times the matrix of v. So it looks like something like a matrix product where the matrices are vectors arranged like that. Okay, sorry. Coming back to the continuous functions. So we saw for Rn, you take uk and you add it to vk, and then you sum up over k. And so we do exactly the same thing. We take the xth coordinate of u and we multiply it against the xth coordinate of v, and then we add up all the coordinates, and that gives us a perfectly well-defined inner product. So, surprise! The integral is useful because actually it's an inner product and it gives you a way to understand geometry. Bet you didn't see that one coming, right? Anyways. Oh, and we're on the interval from 0 to 1. So that's the integral from 0 to 1. Okay. So that is a little blurb about what inner products are. And then whoops, if I can spell it right, the adjoint of T is the unique linear map in, let's just say T star from W to V that satisfies this idea right here, that the inner product of TV and W is going to equal V times T star W. So it's a theorem, and an important theorem, that this exists. Okay, and so notice also that this inner product here, this happens in W, so W needs to be an inner product space. And this one here, this inner product happens in V. So V also has to be an inner product space. And in case I didn't mention it, an inner product space is just a vector space that has an inner product defined on it.